We treat electricity as a commodity summoned at the flick of a switch, but 2 centuries ago, this force was a mysterious novelty used to entertain the wealthy elite. To harness it, humanity needed to bridge the gap between abstract science and practical engineering. In the early 1800s, that bridge seemed impossible to build. Science was the domain of wealthy aristocrats who viewed the universe through the lens of complex Newtonian mathematics. If a phenomenon could not be described by an equation, it was largely dismissed. Michael Faraday was the ultimate outsider to this establishment. He was born into poverty, possessed no mathematical training, and left school with only a basic ability to read and write. His father was a blacksmith in poor health, and the family often struggled to afford food. At 14, Faraday's path seemed set when he began an apprenticeship with a bookbinder. In a society defined by rigid class structures, he was expected to remain a tradesman. Faraday began to read the volumes he was hired to bind. He spent his few spare pennies on scrap metal and glass to recreate experiments in the back of the shop. This obsession led a customer to give him a ticket to hear the chemist Sir Humphry Davy lecture at the Royal Institution. Faraday recorded the lecture in over 300 pages of meticulous notes, bound them in leather, and sent them to Davy. When a laboratory explosion temporarily blinded the chemist, he hired Faraday as a low-level assistant. This uneducated apprentice had moved from the slums to the center of British science. He was now positioned to challenge the mathematical elite using nothing but his own physical observations. In 1820, Hans Christian Ørsted observed that an electric current could cause a nearby compass needle to move. This proved that electricity and magnetism were linked, but no one could explain the geometry of the force. Elite scientists assumed the force traveled in straight, instantaneous lines. However, as this diagram shows, those linear assumptions did not match the results. The needle didn't point toward the wire, it twisted sideways, baffling those who relied solely on traditional formulas. Faraday, unencumbered by these mathematical assumptions, visualized the force differently. He saw invisible circular lines of force swirling around the electrified wire, creating a continuous pull rather than a straight-line tug. To test this, he placed a permanent magnet in a pool of liquid mercury and dangled a wire into the liquid from above. When he connected a battery, he provided the first physical proof of his theory. The current forced the wire to rotate in a continuous circle around the magnet. Faraday had used electricity to create mechanical motion, resulting in the invention of the electric motor. He had solved a mystery that stumped the era's best mathematicians by relying on physical intuition and direct observation rather than existing equations. This success triggered a professional backlash. Sir Humphry Davy, fueled by jealousy, accused his assistant of plagiarism. The fallout was so severe that Faraday stepped away from electromagnetic research for nearly a decade. After Davy's death in 1829, Faraday returned to the laboratory. He was convinced that nature was symmetrical. If electricity could produce magnetism, then magnetism had to be capable of generating electricity.
In 1831, he discovered the missing ingredient, motion. As shown here, a stationary magnet does nothing, but moving the magnet through a coil of wire forces electrons to flow. This demonstrated the principle of electromagnetic induction. He applied this discovery to create the Faraday disc. By spinning a copper disc between the poles of a horseshoe magnet, he produced a steady flow of current, creating the first electrical generator. By proving that mechanical energy could be converted into electricity, Faraday provided the technical foundation for the modern power grid. Faraday now turned toward a deeper question. How do these forces travel across empty space? The scientific establishment believed in action at a distance, where forces instantly reached across a vacuum without any physical medium. Faraday disagreed. He used iron filings to demonstrate that the space around a magnet is occupied by a physical web of force. He called these lines of force, arguing that the interaction happened through this invisible field rather than across an empty void. He then looked for a link between magnetism and light. In 1845, he proved that a powerful magnetic field could twist a beam of polarized light, suggesting that light itself was a vibration on this same invisible web. Despite these discoveries, the academic elite remained skeptical. They viewed his lines of force as a poetic metaphor rather than science, because Faraday could not provide the mathematical proofs required by the Royal Society. At the same time, Faraday's health began to decline. Years of exposure to chemical vapors resulted in severe memory loss and exhaustion. He had modeled a new physical reality for the universe, but he lacked the mathematical language to convince the establishment he was right. The translation finally came from James Clerk Maxwell, a brilliant Scottish mathematician. Unlike many of his peers, Maxwell recognized the physical truth in Faraday's experiments and began the work of turning those observations into formulas. Maxwell translated Faraday's physical lines of force into the elegant equations shown here. These formulas demonstrated that electricity and magnetism move through space as waves within a unified electromagnetic field. When Maxwell calculated the speed at which these waves travel, the result matched the known speed of light. This confirmed Faraday's earlier experiment. Light is an electromagnetic wave, moving through the very field Faraday had visualized. Faraday's intuition was now supported by the highest level of mathematics. The scientific community finally accepted that the forces of nature were unified, a concept that became a cornerstone of modern physics. Faraday spent his final years in a house at Hampton Court provided by Queen Victoria. Though his memory faded, he remained humble, declining a knighthood and preferring a simple burial over a place in Westminster Abbey. His legacy is present in every aspect of modern life. Every power plant, regardless of its fuel source, relies on the principle of induction he discovered, with a copper disc and a magnet. Michael Faraday rose from absolute poverty by trusting his own physical observations over the rigid theories of his time. He saw a physical world that others ignored, and in doing so, provided the power that defines the modern age.